thermocouple time constant experiment. So the goal of this experiment was to determine the time constant of a thermocouple's transient response to temperature changes. And this can be determined mathematically using the following equation if the heat transfer coefficient is known, which is the total heat of the system is equal to the convective heat transfer coefficient times the area times the surrounding temperatures minus the instantaneous temperature. Though this is an easy equation to use, it's not always known that we know the heat transfer coefficient. So in order to determine the time constant, we need to use the lump capacitance method instead. So there are some assumptions we need to make to be able to use the lump capacitance method. The first is that it's valid for uniform temperature changes, and this can be seen mathematically by considering the Biot number, which is the ratio of convective heat transfer to conductive heat transfer being less than or equal to 0.1. We also need to assume there's no internal temperature gradient, which means that there's no energy inside of the system or being generated within the system. And using this assumption along with assuming constant properties allows us to reduce the previous equation to being the volume times density times the specific heat times the change in temperature over change in time equal to our negative heat transfer coefficient times the area times the instantaneous temperature minus the surrounding temperatures. And we can normalize the temperature to make it the instantaneous temperature minus the surrounding temperature divided by the initial temperature minus the surrounding temperature equal to the exponential of the negative time times the heat transfer coefficient times area divided by the density times volume times the specific heat. So considering the lump capacitance solution, we can take the exponential portion of it and get the time constant, which is equal to 1 divided by the heat transfer coefficient times the area times the density times volume times the specific heat. Replacing this into the previous equation gives us an equation for time, which is time equal to the negative time solution times the natural log of the normalized temperature. And plotting these results will give us a line with the slope equal to the negative of the time constant. And the larger the time constant is expected to have a slower response to the body. For the experiment, we used a 1/8 inch type K thermocouple probe and cooled it in an ice water bath. Once it reached the uniform temperature of the ice water, we removed it and dried it, and it was important to dry it to make the surrounding temperatures equal to the room of the temperature and not average temperature of the water that was on the thermocouple with the surrounding temperatures. And we also set it aside from external heat sources for the same reason, to make the surrounding temperatures equal to the room temperature. And then we plotted the temperature change and reported it with respect to time. So the results gave these three graphs. It started with the raw temperature, and then taking the normalized temperature, it basically flipped the graph. And then taking the natural log of the normalized temperature and plotting this with respect to time gives the natural log graph. And using the linear curve best fit, we can get the equation of y equal to negative 372x plus 239.6. So taking the last graph into consideration, we can approximate the time constant to be 372. And since the equipment was in good condition, we can trust that the results were valid in condition of the equipment sense. But some possible discrepancies would be the movement from moving it from the water to setting it aside. Because as it moves in the air, there's more particles that hit it, which pull it faster. And another way to increase our accuracy would be to repeat the experiment multiple times to get an average and standard deviation. And we could also do the experiment with boiling water instead of cooled water to see the difference that this would have on the time constant.